Hello there, my name is Ben and welcome to this math video tutorial. Today we're going to talk about conditional, biconditional statements and a little bit of negation with Dave Morgan's laws of logic. So let's go back to probably a previous video that we did where we did touch base with conditional statements, and symbolically we know that this represents if P then Q, and then P you can think of as, it's like the hypothesis, or some people call it the antecedent, and then the Q is like the result or the consequence of what happens. So we learned, from the truth table, if we construct that very fast, you have P and then Q, and then P implies Q, or if P then Q. So P we had T, T, F, F. Q we got T, F, T, F. So we know if P is true and then Q is true, then P implies Q is true. If P is true and Q is false, then P implies Q is false. And then if P is false, it doesn't matter what Q is, whether it's true or false, that's going to be true. And then the same thing for P is false, Q is false, that's also going to be true. So the only case where if P then Q is going to be false is when P is true and Q is false. That's the only case where we're going to have a false result. So that's how the conditional statement works. And we also touched base briefly on the converse. So that's just reversing the roles of P and Q. Now Q is the antecedent and P is the consequent. And if we review that truth table really fast, we got our Q, and then we got our P, and then if Q then P, or you can say P implies Q, either way. So you have T, T, F, and F. P is TF, TF. So T implies T, that's true. T implies F, that's false, right? Just like we did before. And then with false being the antecedent, that's always going to be true. Now, the thing is that the reason we got the same result as above is because we switched the roles of Q and P. But if we compare them right next to each other, just going this way, just looking at Q and P right here, what we have, T and T, we get T. F and T, we get T. T and F, that's going to be the F. And F, we get T. So you can see that P implies Q. The conditional statement is not the same as the converse. Q implies P. So TF, TT versus TT, FF. So you see those are not logically equivalent. I mean, of course, there are some cases where the conditional statement and its converse are true, but it's not a logical equivalence, as we could see right here. We also went over briefly the contrapositive, and the contrapositive is basically taking the converse and negating the antecedent and the consequent. So we'll actually compare briefly the conditional statement and the contrapositive. we'll see that those are going to be the same. So T, T, F, F, T, F, T, F. So we're going to get the same results we did here. T, F, T, T. And then for the not Q implies not P, we're just going to have to take opposite truth values. So this is going to be false. Implies false is true. True implies false, that's false. False implies true, that's going to be true. And true implies true, it's true. So we see we get exactly the same thing. So the conditional statement and its contrapositive are logically equivalent. And remember that we denote the logical equivalence with using triple equal sign. Just like that, right there. Another one I want to go over is what's called the inverse. And the inverse is just basically taking P implies Q and just negating the antecedent, which is P, and the consequent Q. So you're just going to get not P implies not Q. So this is pretty much, you can probably see that the inverse is going to be logically equivalent to the converse, right? Because if we take the converse, Q implies P, and we take the contrapositive of that converse, we should get the inverse, not P implies not Q. So let's verify that here. Let's see, not P, that's false. Not Q is false, so that's true. Then we got just taking opposite truth values. True implies false, that's false. False implies true, that's true. And then true implies true, that's true. So TF, TT, we got TF, TT. So we can see those two statements are logically equivalent. So the converse is logically equivalent to the inverse. Alright, so we covered the conditional statements, did a little bit of negations with converse, contrapositive, and the inverse. Now we're going to look at briefly what the bi-conditional statement is and what that means. So, bi-conditional, since bi means two, that means we're going to have two different directions, two different arrows going this way. And so, we have P, and then we have that, left and right arrow sign Q. And so this means this is like P if and only if Q. And some people abbreviate if and only if. They'll say IFF just for short, if and only if. And the way that we can express this, this logical statement right here, P if and only if Q, we can do you could say this is logically equivalent to if P then Q, and then we have and Q, if Q then P. So that is how we could express that. So we could draw a truth table for that statement. And let's see what we get when we do that. And basically we can copy some of our previous results down, because we already know if P then Q, and we know if Q then P. And then we'll just put P if and only if Q. This will be our result column right here. What we're going to get as a result. So we know with the P's, we just had our T and T, F and F kind of run out of space here. I apologize for that. And then Q is TF, TF. And then the if P then Q, we're just going to copy that down. That's the TF and TT. And then the converse, if Q then P, that's T, T, F, and T. So basically what we're going to do here in this column, the if P, if and only if Q, we're just going to take the and statement of the conditional and its converse. And you know, if both of them are true here, T and T, you know that's true. The false and true, that's false. True and false, that's also false. And then true, true, that's true. So we get TFFT for our result for the biconditional statement. So you can see this is not quite the same, you know, as if you did the converse and the conditional statement. You get something different. So sometimes you may have a statement that is true one way, and then the other way it's not true. So the conditional statement, if P then Q, is if that's true, it may not be true that, you know, if Q then P, it's not true. So, you know, for example, you know, you may say if it is raining, then the ground is wet. You know, if it is raining, yeah, the ground's probably wet. That's probably true. But if you think about the converse going the other way around, you know, if the ground is wet, then it's raining. You know, the ground may be wet, but it doesn't necessarily mean it's raining, because, you know, someone could just use a water hose to wet the ground or pour some water on the ground and it's not raining. So it doesn't always work both ways. So we've talked about biconditional statements here. Now we're going to talk about the negation of some of these statements, and we'll be there just a moment. Okay, so let's get a new board here, and let's talk about negations. So we've learned the and statement, the or statement. So if we start with the and statement, let's say P and Q. Some people call this the conjunction for and. And if we want to negate this statement or make it the opposite truth value, basically doing not of P and Q, then we're going to say that this is logically equivalent to the or statement, but we're negating each of these P and Q statements here. So we're going to negate P and Q, negate both of those, and then we're going to change the and to an or. And the or is called a disjunction. So and is the conjunction, and we'll just write that here, conjunction, that's an O. And then the or here is called the disjunction. So you can basically say that the negation of the conjunction is the disjunction of those negations. So another negation that we could use is the or statement, P or Q. And that's going to be logically equivalent to, you probably guessed, now that we're using the or, the disjunction is going to be the conjunction of those negations. So not P and not Q. So we always just negate each individual statement, and then we take the opposite logical operator, in this case the opposite of the disjunction or is the conjunction, which is and. So those are two of very common, what are called De Morgan's laws with logic. The not P and Q is equivalent to not P or not Q, and then the not P or Q is logical equivalent to not P and not Q. Now what if we want to negate a conditional statement? Say we want to negate, and we'll use the tilde this time, kind of mix it up. So if P then Q, or P implies Q. So your question is, maybe the negation of a conditional statement is another conditional statement, but that's actually not true. It is logically equivalent to, what we're going to do is we're going to take P, the antecedent, and we're going to change this to and then we're going to negate the consequent, which is not Q. So that is the negation of a conditional statement. Not P implies Q is the same as P and not Q. Okay. So let's see, what about something like the converse? We could negate the converse if we wanted to. So that's Q implies P, just reversing the roles of Q and P. Q being the antecedent and P is the consequent. So we could have Q, say Q, we affirm that, and then we say and, not P. So Q and not P. What about the negation of the inverse? Let's say not P implies not Q. So basically we're going to keep this the same. This is not P. And then we're going to do and take the opposite truth value of not Q, which is Q. So not P and Q. So that would be the negation of the inverse. And then how about the contrapositive? We know that if P then Q, we know the contrapositive is not Q, implies not P. And so that's going to be logically equivalent to not Q. We keep that the same. And take the opposite truth value, not P, which is P. And notice that it's the same, right? P and not Q is the same as not Q and P. So it's important to know that with the and or statements, that if you have two statements, just call them like A and B. So you can say A and B, this is the same thing as B and A. Same applies for A or B. It's the same thing as B or A. So these statements are like the commutative laws, kind of like with addition, A plus B equals B plus A. And then with multiplication, A times B equals B times A. It's just like in algebra. So these laws exactly apply in the logic. So, there's lots of other De Morgan's laws too. We can mention a couple more. These aren't necessarily negation laws, but we could go over those. Let's see here. We'll start a new board and just go over some other important laws before we end our video here. So other laws. So these are more compound ones. So let's say you have three statements, P, Q, and R. So you could say P and Q and R. This is logically equivalent to P and Q and R. So this is the associative law for and, just like with addition, when you have three numbers, or with multiplication with three numbers, you can group them, any two out of the three, as long as you have the same operator, which is and then the same applies for or as well. P or Q or R is the same as P or Q, these grouped together, or R. And also there's some so those are the associative laws. There's also, let's say, P and Q or R. This time we can't do the associative law because we have two different operations. So this is more of a distributive law. So we have an and then we have an or inside the parentheses. So we're going to distribute the P to the Q and say P and Q to C's. And then we'll do the operation of or. And then distribute the P to the R, so that's P and R, parentheses. So that was P and Q or R is the same thing as P and Q. or P and R. We can also do P or Q and R. So same idea, just different operations this time. We have the or outside, the and inside, so it's logically equivalent to P or Q and P or R. So those are the distributive laws. Let's see here. There are some other laws that we could do or go over. Let's say we went with tautologies, like if we had a statement P and let's say and a tautology T. And see what this is equivalent to. And the way we can do that is construct a truth table here. So we'll have P for one statement, T for the tautology, and then P and T. See what that result is. So for P we have T, T, F, F. And a tautology, so we went over earlier, that's true regardless of the individual statements that we have. So these are all true. And so if we get T and T, we get T. T and T, we get T. F and T is F. And F and T is also F. So notice that P and T, the tautology with P, T, T, F, F is the same thing as the original statement P, T, T, F, F. So we can say this is equal to P. And then let's go over P or T, tautology. See what that's equivalent to. See if I can squeeze it in here. It's P or T. So we're looking at the or this time. So we have T or T. T. T or T is T. F or T is still T. F or T is still T. So we get all T's this time, which match up with T, the tautology. So we get the tautology T. So if it's statement P in the tautology, you're going to get a statement back, P. And if it's P or the tautology, you're going to get the tautology back. So you can also look at P and let's do the contradiction. And also P or the contradiction. We'll call that C. And we construct another truth table. And this will be the last one we'll go over here. P, C, P and C, and then P or C. So we have P's, T, T, F, F. C is a contradiction, so we have false for every case. So then P and C, T and F, that's F. T and F is F. T and F is F. Or sorry, F and F is F, and still F and F is F. So we get false every time, so that gives us the contradiction. So we get C. And then P or C, let's see, you probably will guess what that is. So T and or F is T, since it's or, T or F's T, F or F is F, and F or F still F. So T, F, F, that matches up with the P statement, T, T, F, F, so we get P. Okay. So, you know, as an exercise when we're talking about the bi-conditional statement, make sure that, you know, when you had P, if and only if Q is the same thing as P, if P, then Q, and if Q, then P. Go through an exercise where you have to find the negation of the statement right here. If P, then Q, and if Q, then P. And so I'll let you try that one on your own as far as find the negation. Just using just what we learned earlier, you know, using that it's and this time, yeah, P and Q. So remember, when you take the negation of P and Q, you're going to get not P or not Q. So you're going to know what kind of operation this will be, and then you just negate each of these statements separately, and that'll give you the negation. So I'll let you try that for practice. Well, this has been for this math video tutorial on conditional, biconditional, and negations, and we cover some other De Morgan's laws of logic. Do stay tuned for the next video, and we will probably cover more with this, perhaps do something with sets, talking about sets, set logic. So thank you for watching, and hope you have a good day. Take care. Bye-bye.